Thanks very much. So let's get into it. So today we're going to talk a bit about bridge security and cross-chain security. This is going low. Just a second. Yeah. And to introduce the topic of security, we're also going to discuss a specific bridge implementation we're conducting at Blockdaemon called Blockdaemon and Metacraft Labs, which is a SNARKS-based light client. That's the infrastructure to build secure bridges. So after we introduce this type of bridge we're constructing, then we'll talking about how to protect those bridges and how to do bridge security with Hephaestus, which is our recent paper. This has been joint work with INESC-ID, Técnico, Hyperledger, and Accenture. And I'm here representing my university and also Blockdaemon, where I work at as a research engineer. So why shall we study bridges? Well, there's a lot of industry and academic interest for different bridges. There are currently over 100 bridges, but here in this figure, you can see the main ones ordered by total value locked. And we have been assisting to a very dynamic, evolving ecosystem of cross-chain solutions, namely bridges that allow to transfer tokens. But besides transferring tokens, cross-chain solutions are useful in other ways. For example, offloading transactional computations to different infrastructures, allowing to scale. So scalability research is, in fact, at least partially, interoperability research. Besides, we can study interoperability in the perspective of security. So how can we peg our weaker chain or centralized system to a more decentralized system to promote better security? How can we migrate our decentralized app, our infrastructure, to another blockchain in case there has been a hack or in case there are more interesting features on another blockchain? And typically, the biggest advantage of enabling interoperability across blockchains is leveraging cross-market efficiencies, encouraging interactions across communities, moving liquidity across blockchains, and also doing or exploring synergies at the application level, like cross-chain tokenization. Also, for example, cross-chain governance, something that Uniswap is currently exploring. But unfortunately, bridges have been constantly and consistently hacked throughout the last 2 years. We've been assisting to millions and millions and millions of dollars, more specific, around 2 billion, 1.5 to $2 billion lost for hackers or lost by hacker attacks. So we can see in this graph that the total value locked at its peak by bridges was around $25 billion, which is considerable. And we've also assisted to plummeting of that value when the different major bridges were hacked. We can see the Poly bridge, Wormhole, Ronin, Nomad hacks, and their influence on the total value locked. So we need more secure bridges. Which ones should we pick, or which direction of research should we follow? It's not an easy, there's no easy answer because there's such big variety. However, there are a couple studies, actually by now, a lot of studies comparing systematically cross-chain solutions and cross-chain bridges. Some are more academic in nature, like our 2021 survey. Some are more directed towards industry use cases, such as the Bridge Assessment Report, which I recommend you to read. It's very recent, just was published a few days ago, sponsored by Uniswap Foundation, where the authors explore the ideal interoperability infrastructure for cross-chain governance. Our survey is a bit more general, explores more diverse solutions. So if we focus specifically on the bridges, because we have more interoperability solutions than bridges. we can divide bridges in three categories: externally validated bridges, light client bridges, or locally verified, actually natively verified, sorry, and liquidity networks that are locally verified. Externally verified bridges rely on a quorum or a single party to validate messages on the source chain. Liquidity networks utilize typically hash time lock contracts, which are expensive. And on the other hand, light clients utilize a light client algorithm implementation as a smart contract on a target chain to validate facts that occurred on a source chain, such as transaction inclusion. And we are interested mostly on these type of solutions because they do not introduce any trust assumptions rather than the underlying bridge, the underlying chains are secure, and the cryptographic protocols that we use to implement the light clients are secure.
Can I ask a question?
So some,
sorry.
Yeah.
So with
Yes, of
these
course.
three types, do we know if one of the types is more used in certain applications, where it's more likely, or it's more likely evenly spread out across applications that there's just three types of validations?
So the main applications are token transfers, and the different solutions are relatively spread equally towards implementing token transfers. There's, according to what we've seen, a trend to move more towards the light client and natively verified solutions in the industry because they're the most decentralized ones, rather than externally validated and even liquidity networks. This is because if you're securing billions of dollars, if only, let's say, 2 out of 4 validators are securing billions of dollars, it's a no-brainer that attackers would try to target those nodes, especially if they're public, which has happened in the Ronin hack, for example. So in principle, these light clients are a bit harder to they're more secure by construction, but of course all bridges might have implementation errors and bugs, and so there's no solution that's completely secure, which is why we've developed Hephaestus. So light client is a system that validates block headers from external blockchains. Those block headers contain a Merkle tree root, which is called a state root, which can be used to run Merkle proofs against. Those Merkle proofs are all proving facts. So that's the idea of light client. It provides the state root from the block header that we will use to validate Merkle proofs. Then we have the relayers. The relayers are off-chain components that relay information across chains. So when we did our survey in 2021, a relayer was mostly seen as the entity that relays only block headers. But as the industry evolves, people are using the relayer term also to refer application relayers. So off-chain applications that relay Merkle proofs. So we have essentially two types of relayers: the ones relaying block headers and on-chain information, and the ones relaying off-chain information or applicational data. So in our example, we'll have the Dendrith relayer that creates proofs off-chain and sends it to the light client verified on-chain. And we'll have an application relayer that creates proofs off-chain, namely Merkle proofs, and sends it to the smart contract using Dendrith. Two relayers. Another concept we need is the concept of contract storage. So in Ethereum, smart contracts store data in memory or in storage. Storage is persisted on the blockchain. It's more expensive than storing it in memory because that storage is replicated across all nodes, and the storage is a key value store. So the use case we're picking is the use case from a paper called Smart Sync, which I recommend you to read. This figure is from that paper. And the idea is that we have a state, origin state on the blockchain A. So we can see that the initial state is A = 5, B = 3. And we have state transitions when we are applying different transactions to this state. So this value A is evolving from 5 to 6, then 7, then 6, and the B's are also evolving. So you have initial state, transactions, state transitions, and the final state, or let's say our current state. The idea is to synchronize this state, or to, in a sense, migrate these states to a target blockchain. And the underlying idea is that you do not need to sync the state at every transaction, at every single transaction. You can do it in batches. So instead of doing 3 updates, you can do 1 update and still have the latest state. So what we're proposing here is a light-line system that allows to create cross-chain logic or cross-chain use cases. And the use case we're going to showcase is a state synchronization and not an asset token transfer, which is, let's say, the canonical use case to explain bridges. We have a smart contract, a very simple smart contract. It's so simple that it's called simple storage, and it essentially, it's a key value store. It stores variables, and it also has a mapping, but we're mainly going to be interested in these very simple variables that the contract stores. So the idea is that the user on the source blockchain, which is Ethereum, will transact against this smart contract, for example, changing the value of A. Then an off-chain relayer sees the change in the smart contract, namely by analyzing the transactions that are confirmed on the Ethereum network. And then it tries to replicate the state by sending the information that was changed plus a proof, a validity proof that that state transition is valid on a target blockchain. Excuse me. So capture updates, generate proofs of updates, and then send the proofs with the transactional data to the source chain.
I'm sorry, I think we have a question in the Q&A. How do we determine the frequency for sync?
Okay, so we're going to talk a bit about it, but essentially you want to synchronize the use case. So there's the trade-off between liveness and cost. The more synchronizations you do, or the higher the frequency of synchronizations, the higher the cost you'll have, because the more on-chain transactions you have to submit. So you could choose to batch your syncs, or you could choose to, periodically sync every state transition. For the majority of use cases, it's admissible to batch updates and synchronize more sparsely instead of for every single transaction. Okay, thank you for the question. Please put questions at any time. All right, so a proof in our context is a Merkle proof. A Merkle proof allows to prove inclusion of data in this tree-like structure. Ethereum uses Merkle proofs, Merkle trees to represent its state. So accounts are represented as Merkle trees, which are included in the block headers. Those accounts have on their turn Merkle trees that represent the storage of that account. So if we want to prove transaction inclusion, let's say a transaction L that is represented as a hash, the hash of L, HL, or actually we can take HK because it's the current example. We only need to provide HL, HIJ, and 2 more hashes. So a Merkle proof is a path between the information or data we want to prove inclusion of and the root of the tree. So we can provide the data itself and 4 hashes, and in algorithmic time, the verifier can recursively hash the whole elements up to the tree, up to the root of the tree, and if they coincide, it means that the proof is valid. In practice, in Ethereum, it's a bit more complicated because instead of a binary tree, which is a trusted root on a trusted Merkle tree root for them to be valid. So if we provide a false or a fake Merkle root, it is possible to prove fake, to falsify proofs, or to have valid proofs that are not verified correctly. So we need a trustable state root, which is the goal of the light client, to provide a valid state root, which is what Dendrith, the system we're proposing, does. So it takes a beacon chain block. Then from that beacon chain block, it takes the execution layer state root. And with this, it's possible to authenticate any state variable via a Merkle proof. So Dendrith is an on-chain implementation of the beacon light client syncing algorithm that's done by mainly Metacraft Labs and also Blockdaemon, which provides these valid state roots. Now, the interesting thing is that we assure that those state roots are valid by implementing these verification steps, this verification logic, which is the Altair light client sync algorithm, in a zero knowledge circuit. So we design the zero knowledge circuits, and then we create SNARKS, which are proofs that the zero knowledge circuit algorithm has been correctly executed. And these outputs these trusted state roots. So we have two different kinds of proofs: the SNARK proofs to verify the state roots, and the Merkle proofs, which will be done against these verified state roots. So this is the general pipeline of generating a SNARK. You have an idea, which is the protocol specification. You implement it as a program. Then it does some arithmetization by transforming the program into a ranked 1 constraint system. You run a public setup, generates a couple of parameters, and then you can use the input you want and those public parameters to generate a proof, a SNARK. That proof is able to be verified on chain by using the rapid SNARK or the SNARKGS actually library, and it will output true or false, depending if the input you've provided against the algorithm matches a certain output. Right? So the program is process a light client update by applying all light client syncing rules, right? And basically an operator can supply a proof of correct execution for a particular update. The output of this process is the execution state root, the finalized state root, and an optimistic state root. We are interested in the execution state root, which is this Merkle root. Right, so these are a couple details. It's actually Rapid SNARK that generates the proofs. We also generate automatically, or the framework generates rather, a verifier solidity smart contracts. So when we are generating the SNARKs, we can transact them and put them on chain, and they are verified by this contract. So we can compose smart contracts to execute cross-chain logic only if this verifier passes the verification of a certain SNARK. So this is the architecture. We have the Ethereum beacon chain. We have a smart contract there, which is our application. In our case, it's the simple storage contract. Then we have two relayers. One of the relayers on top, it's the Dendrith relayer. It obtains data from the Ethereum beacon chain, namely the previous blocks, the sync committee validators, and so on. And it validates a proof that a certain light client update is valid. On the other hand, we have our application of relayer, which basically takes the most recent updates and generates a Merkle proof for those updates. Then the light client sync relayer submits those SNARKs on chain, and as the output, we have validated state roots, which are available. We have a list of state roots that are valid and available on chain. On the other hand, the off-chain relayer submits the Merkle proof and the data to the application on the target chain, which validates the Merkle proof on a third-party library that verifies Merkle proofs, and that Merkle proof verifier obtains the state roots from the Dendrith SNARK verifier contract. So this is the way to compose these two different types of proofs, such that the state roots are derived in a trustless way, hardened by cryptography behind SNARKs, and Merkle proofs as well. And these Merkle proofs component. Any questions so far? Feel free. All right, let's keep going. So if we zoom in this left part of our use case, we can see the process in a bit more detail. First, we can look at the right side. So the Dendrith off-chain relayer calculates a new state root and creates a proof for that state root. It sends the proof to the on-chain verifier, and the on-chain verifier stores a list of validated state roots. Okay. On the left side, we have a couple steps. So first, the user updates the source contract. So you update a storage variable like A or B, and you get a Merkle proof for that update. Okay. Then the user, or an application on behalf of the user, updates the same value or does the same update on the target chain and gets a proof of that update. So the updates on both chains and both smart contracts are done without the verification yet, but they're done in sequence. So we first update one contract and then we updated the other contract. The verification part happens afterwards, where we submit two Merkle proofs against this relay contract that will verify both proofs and use the verified state root in steps 8, 9, and 10. So essentially, what this means is that you could do an invalid state synchronization, but the verification will not pass on the relay contract. So instead of enforcing the state synchronizations to be valid, we allow anything to happen, and at the end we verified that the state synchronization was valid. Right? This is the use case that SmartSync proposed. It's a slightly different model because you may have expected that the verifications would be enforced before the update on the target contract, but it's not the case. It's another model. It allows for a bit more flexibility, which is fine. One of the secret sauces of this paradigm is that the storage hashes of the Merkle proofs, when we're verifying both Merkle proofs, they are compared, meaning that if the storage on the source contract is different from the storage on the target contract, we'll have a mismatch, and the verification phase will not be successful. This means that we are enforcing on the verification side that the Merkle proofs are correct. The Merkle proofs are based on the state root that is validated by the SNARKs, and the storage hashes of both contracts match, meaning they have exactly the same storage. Of course, that this use case only applies for EVM-based blockchains, because for other types of blockchains like Hyperledger Fabric or Cosmos-based blockchains, the way to construct the storage of a contract might be different from Ethereum, namely EVM-based chains. Okay. So from the smart contract synchronization to a token bridge, we can, at its foundation layer, we can do a couple of changes. Instead of having a transaction setting the value of A, we'll block tokens. and we would unlock tokens on the target chain. So this showcases that different cross-chain applications can be built on top of our system. Okay. So the problem here is that no matter how carefully you implement your bridge, no matter how tested your protocol is, your bridge or cross-chain application will eventually get hacked or eventually get exploited, at least in the initial phases of exploration where the technologies are not mature. So instead of being completely obsessed by security, which we should be, by the way, we could also invest heavily on monitoring and proactive security. So, and also reactive security. I mean, when something happens, we minimize the damages. And this is the Hephaestus part of the paper. It addresses bridge risks and challenges. So we have implementation risks, we have financial risks and crypto economic risks, and we have lots of open issues which also are related to the possibility of new attack vectors being explored. So some of the most common risks and challenges are bugs on the protocol or bugs on the implementations of the protocol, which we have seen in these recent breach hacks. Furthermore, regulation is legal is not very well explored, so it's not very clear what happens if a breach is hacked. Who is responsible? Is it the implementation team? Is it the breach? Are the users going to get reimbursed? So there's also all sorts of legal implications and considerations that we may bring on the table for studying these challenges.
Sorry, can I ask a question?
So there are.
So if we're thinking about these risks, is there a way we're going to quantify these, or it's more like how do we, for example, compare implementation risk with financial risk? Or is there a way we can do that? Or?
Excellent question. Excellent question. So yes, there is a way to do that, which is the next slide. So some frameworks developed not only by us, we wrote this paper, Do You Need a Distributed Ledger Technology Interoperability Solution? Which proposes a framework to systematically compare interoperability solutions and therefore risk. There's also this breach assessment report from Uniswap I have referred, which does exactly this quantification. So the authors have proposed a set of criteria that compares breaches in terms of implementation risk, operational risk, network risk, and it allows basically assigning a score to each blockchain, to each breach solution, which is a more systematic way to approach at least risk prevention and operations, DevSec operations. We also do this partially and internally at Blockdaemon. We've been developing a complementary framework to the bridge assessment framework, which essentially evaluates data transfers because their use case is cross-chain governance. It leaves a bit out the token transfers. So yes, there are several frameworks, several ways to evaluate these risks. Some in academia, some in the industry. So we eventually figured out that we need to mitigate implementation risk, and there's a varied set of techniques in the academia and industry. We proposed Hephaestus, which is a security by specification methodology to mitigate implementation risk, and in this part of the presentation we're going to discuss how this is exactly done. So we have 50 minutes, right? So half an hour has passed. I think we're quite on time.
Yes,
All right, so the underlying concepts we take as the foundational base for our paper is the concept of event log. An event log is a set of events a set of event entries in a table or in a database such that they represent a process or a real life situation. In this example, excuse me, in this example, we have represented the process of selling phones in a store. We can see that they have an order number, activity, timestamps, and something called resources, which are basically attributes of the process. Note that we have the timestamp, and this is interesting because basically by analyzing the timestamps, we can infer orders between activities, right? The activities are sort of an identifier for the for the part of the process or for the step of the process that's happening. And we have a special number, which is the order number, a sort of unique identifier or primary key in the database, in the relational database, if you will, that is called the case ID. The case ID is one of the most important concepts in the area of process mining, which is the scientific area that analyzes logs and constructs what we'll call as models, as the process models for a specific process. Right, so we have case ID, activities, timestamps, and other data. So the idea now is to map this to the cross-chain scenario. So what we've done was to extend the data formats or the data schemas of transactions in different chains, and we extended this to a common format. And this format has a case ID, it has an activity, it has resources. So if you pay close attention to this table, you could probably identify what is the activity behind what is the activity what is the attributes that represents an activity in our mapping, which is the method name. So the method name is the function that your which basically represents the activity or the action that is going to be done in the transaction. Then the transactions have attributes, and those are resources. So in a cross-chain transaction, you have a meta resource, which is a blockchain ID, and then you have specific resources, which are the parameters of the transaction, who created the transaction, the identity, the cost, and you could add more non-native parameters, such as the latency and the carbon footprint, and so on. And it's worth saying that a cross-chain transaction might be composed of 2 transactions, 3 transactions, and transactions. And in this case, it's composed by 2 transactions, one in a permission blockchain, another one in a permissionless blockchain. So this cross-chain transaction would represent a mint token, where we lock a token on the source chain, and we unlock the representation of that token, well, the value, the equivalent value of the locked token on the target blockchain, which is basically how bridges are implemented. They lock a token on the source blockchain, and they unlock a token, a representation of that token on the target blockchain. Also called the wrapped assets. You might have seen when you're using decentralized exchanges, the wrapped assets or the synthetic assets. So typically there are liquidity providers that provide the real assets, let's say, for example, ETH instead of wrapped ETH, and can exchange, they exchange the native token for wrapped tokens in for a fee or for some, or they're incentivized by protocols to do so. The so-called liquidity pools. Right, so we have the event logs, we have the data format. Now we have to do some interesting things. So the magic. And the magic is using process mining algorithms. So basically they're a way to infer causality or causal relationships from the event logs. So basically those algorithms analyze the different activities that I the case ID. So for example, if you look here on the left, you have 99001. And if you isolate, if you do if you filter by case ID, you'll notice that you have a very well-defined process. So you have register order, and then you have check stock, then you have ship order, and then you have handle payment. So these logs, they have the process implicit on the logs, and we can discover that process from the logs without specifying the process directly, which is what happens here. So you have different relationships. So for example, B follows A, so it's a direct following relationship. You have sequence relationships, so B comes after A, but not necessarily right after. B happens, and C happens, and finally it's the case that B happens or E happens. And those relationships are inferred from this L1, which is a log. And this means that the sequence A, B, C, D happens 3 times, the sequence A, C, B, D happens twice, and A, E, D happens once. So you run this algorithm. In this case, it's alpha miner, the first process mining algorithm. And since there has been a vast literature coming with different algorithms. And you basically first construct or derive these relationships between activities, and then from those relationship mappings, you can construct what is a process model, a visual representation of the process, the different possibilities of the process. So A can happen, then B, then D. It's a possibility. Or A, and then E, and then D, and so on. So you might see where this is going. The idea now is to create a process model for our bridge use case. So what you see here represented are the activities that are generated from event logs. The activities are transactions, and then the rules, the cross-chain rules, the cross-chain model are the arrows. So what can happen in the bridge use case? So we are binding local transactions in a single cross-chain transaction that respect a certain set of rules. And this is how we try to model the bridge use case. This is a bit maybe orthogonal, but we can also do very interesting business analytics on top of cross-chain transactions. Give me just a second. Someone's chopping a tree like really enthusiastically. So now we can take this model, and we can basically analyze, monitor incoming transactions in real time, and discover what are their throughput, what are their latency, what are their costs, what are their revenue. You can build interfaces for people to identify what is precisely the step of the protocol or the step of the process model that they're currently in, and you can have a better control, fine-grained control over your use case. So first, on the bridge, we have an asset initialization, then we have a lock, and then we have the rest of the process. So the idea for monitoring is that we construct this cross-chain model, and then we are monitoring incoming transactions. So this is basically the sequence we are expecting to see from the model, from previous observations, or from specification. And in this cross-chain model, the bridge is effectively implemented between steps 2 and 3, meaning that after a lock on the source blockchain, we'll have a mint on the target blockchain. So in a case that we did not have a lock, but we had a mint, it means that our cross-chain model has been violated. The transactions we are seeing incoming do not match the model, which is represented in this diagram. So instead of having 1, 2, 3, we have 1, 3, meaning that there is a step that is skipped. When this happens, we can emit an alert, and we can freeze the bridge as a reaction that aims to mitigate the damage caused by this attack. Note that this might be an attack or might be under specification of the model, in which case the alerts are good because it shows that we are missing something, or there are executions paths that we were not predicting in the smart contracts, which often happens when they're very complex, or they are identifying effectively attacks. So this is the algorithm that does the same, basically. So each time a transaction happens, we are updating the state. We verify that the new state conforms to the cross-chain model with this verify satisfiability function, and basically, if the transactions that are incoming in the form of events, we call them events here instead of transactions, if they conform to the model, then we update the model and by creating a new cross-chain state. So we have cross-chain state, transaction, new cross-chain state. And after we create the cross-chain state, we just return the new state and we say everything was fine, the cross-chain rules are being respected. Now, we implemented this idea using Hyperledger Cacti. It's called Cacti now instead of Cactus. We bootstrapped two blockchains, a private Hyperledger Fabric blockchain, a Hyperledger Besu blockchain, and we created events. These events were sent to our cross-chain transaction manager, which aggregated them and runs automatically these process mining algorithms on top of these events, generating a cross-chain model and analyzing if transactions are conforming to this model after generation, of course. So yeah, it's basically what's here. The code is public, and the data sets we used, which are relatively simple because this is a proof of concept. And yeah, it's available at Hyperledger Cacti. So here we are showing specifically what are these cross-chain events and from where we build these cross-chain events. So in case of Hyperledger Fabric, a transaction has all these elements. We map those elements to a cross-chain event, and then we construct a log. Right? So our evaluation shows that processing a large number of transactions is relatively fast. So creating the cross-chain model and evaluating that cross-chain model is quite quick because it's an off-chain process. It's quick to run. On the other hand, launching the infrastructure and issuing the transactions is more costly. Right? Yeah, so the bottlenecks are the on-chain phases, basically. So future work. Use and compare techniques from different disciplines, not only process mining, but also data mining, which are very closely related, I would say, and machine learning for detecting these risks, these false positives, that basically means under specification, or the true positives, which basically mean attacks. We can try to derive the complex subtle relationships between transactions in different systems by applying these techniques, which would enable tracing and fine-grained auditing of transactions. There are a few industry solutions that use this idea to try to prevent attacks, to launch alerts, so, such as Hyperlane. It's a company that does this. So finally, let's conclude. So interoperability has been studied in the last years. It's a complex and error-prone area, and this is shown by the number of attacks and the number of complex research that has been emerging in the last years. We need to not only proactively secure the bridges, but also reactively, meaning that we need monitoring and auditing tools, and we need to mitigate attacks when they happen, and they will inevitably happen. Finally, we didn't talk a lot about this, but we also need standardization across the different interoperability layers, so legal, semantic, technical. And this is also an area of research that we are exploring within IATF, the Internet Engineering Task Force, namely the Secure Asset Transfer Protocol we are developing. Some references, you have access to our paper. It's published as a preprint. Currently, it's being submitted. It's being reviewed, peer reviewed right now. And you also have then there is repository there. So all of this is open source. You can clone the projects. You can run it. You can see how it works. You can export the code. And yeah, hopefully this will help the community protect against attacks. And that concludes my presentation. Thank you a lot for attending and for your attention, and I'll be happy to answer any questions.